Today's guest, Marcus Chown, has spent years tracing the history of black holes, not just the science, but also the brilliant scientists who gave us the knowledge and insight into these marvelous behemoths of space and time. From equations scribbled in the trenches of World War I to a vanishing dark star in the 1970s, Marcus takes us on a journey from discovery to understanding of all that we know so far and what we do not yet know. His latest book, A Crack in Everything, tells the astonishing story of how black holes went from absurd fantasy to perhaps the most fundamental phenomena that shapes our entire reality. Let's go. Marcus, soon I want to ask you if black holes are actually creators, a type of force that acts as a womb, perhaps for new universes, but certainly for solar systems like our own. But first, let's start where everyone starts, as black holes as destroyers of worlds. What makes black holes the most terrifying objects in the cosmos?
Well, they're regions of space where gravity is so strong that nothing, not even light, can escape. So they do have this reputation for sucking in material relentlessly. And this was really a big mistake that physicists and astronomers made over the last century, because they thought that they just suck in material, they're black against the black of space, and they'd be actually impossible to see. But actually, one of the most striking features of, well, first of all, black holes, the black holes that we know of in the universe include some of the most luminous objects in creation, so they're far from being black. And although we can just about see material disappearing down the whole of a black hole, just about, the most striking feature is often of material coming out, often along these titanic jets of material which stab out through galaxies for millions of light years. So really, the idea of them sucking in material is kind of, they do, but actually they kind of defy that picture. And that's basically because they're embedded in an environment, and physicists and astronomers assume that they would be black because they would be isolated. But in fact, pretty much everything in the universe is embedded in an environment. Most stars are binary stars. Our sun is quite unusual, being a solitary star. It's quite unusual. And being embedded in an environment, having a companion, having gas or dust around you makes all the difference. And this leads to these objects being, in fact, incredibly luminous, even though they're black holes.
One thing I really loved about your writing, I always love your writing, but about the book, is that you kind of steer away from the kind of pop culture mythology of, spaghettification. Yes, you mention it, of course, you have to. It's a law of nature, right? But you really get into the hard facts and physics of it, and it's no surprise because of your scientific training and your past books as well. And speaking of books, I like to do what you're never supposed to do on the show, which is a feature called Judging Books by Their Cover. So I actually bought the audiobook and rated it with an asterism of 5 stars. Nothing less would suffice. It's got the encomium that it well deserves from Richard Dawkins, a pretty wonderful book, and from my one of my kids' favorite astrophysicist, also named Brian May. He says Marcus Chown rocks. Wow, you can't ask for a better. So please, that's the back cover, but judge the front cover. Title, subtitle, and this mysterious, monstrous cover art that's so beautiful.
Glad you like it. But I should point out that there are 2 types of black holes. There are the theoretical black holes, which you talk about, which are fantastically important because, our major theories of physics collide in black holes. Our theory of the microscopic world, quantum theory, our theory of big things, general relativity, and thermodynamics, our theory of heat. They clash. And they're not melded. They predict different things in the same domain, which is gold dust for physicists, because when a theory is shown to break down, and Einstein's theory of gravity breaks down in the center of a black hole, then we are encouraged to look for a deeper, better theory. So there's theoretical black holes, and of course Stephen Hawking's name is associated with those. And then there's the real black holes, which are the black holes we've actually found out in the universe. And my book is essentially about the real black holes, because incredibly, not only do they exist, but they're relatively common. And as you said in your intro, they play a role in us having this conversation today.
I need to really understand the nature of black holes. Are they really, cosmic safes hiding away information forever? Are they cosmic shredders obliterating it beyond recovery? How do you, as a popularizer and an explicator, exceptional explicator par excellence, how do you think of these things? How do you think of their paradoxical nature and Hawking radiation, information paradox, firewalls. Talk about how these objects are fascinating in their own right, but made even more so by the many paradoxes that they bring up.
They are paradoxical. As I said, the real black holes in the universe are paradoxical because they aren't black. You know, they are fantastically luminous because of the material that falls into them and the friction, because it turns out that everything in the universe is rotating, the Earth is rotating, the galaxy is rotating, which means material doesn't fall directly into a black hole. It kind of swirls down onto it like water down a plug hole, and friction causes it to heat to millions of degrees, and this is what causes them to shine. But I ought to just point out that black holes are the simplest objects in the whole of physics, because there's nothing, they're made of nothing more than space and time, as far as we know. So I ought to tell you that stellar mass black holes form when a star gets to the end of its life, runs out of fuel, with no fuel to burn, to generate heat, to push outwards. Gravity crushes the star, and as far as we know, it crushes it down to a point, what we call a singularity. And really, the star, as far as we know, actually vanishes. And all that's left is a bottomless pit in the fabric of space-time. This is Einstein's picture. Einstein realized that gravity was actually the curvature of space-time. You know, we can't visualize it because it's a four-dimensional thing. That's why it took the genius of Einstein to realize. So, you know, all there is left after the star has collapsed is this bottomless pit from which nothing, not even light, can actually climb out. But you talked about Hawking radiation. You know, a lot of people get puzzled by this. Hawking in 1974 realized that actually black holes glow. They have a temperature. They are thermodynamic objects, and they glow with this stuff called Hawking radiation that streams outwards. And people are often puzzled because they say, well, surely black holes are defined by nothing ever getting out of them. Well, the Hawking radiation doesn't get out of them. It's created in the vacuum just outside the perimeter of the black hole. So we define this kind of spherical membrane. This is an imaginary membrane called the event horizon, and it's the point of no return for infalling light and matter, and the Hawking radiation is generated on the outside. But I mean, I know the question you're asking me, and that is that as far as we know in physics, information is never destroyed. This is quite fundamental to our laws of physics. And so the question then is, if the star, the massive star, shrinks down to nothing and vanishes, leaving only a kind of bottomless pit in space-time, what happens to the information that describes the star? Tremendous amount of information will be required to tell you the type of atoms, their location, where their electrons are. You know, you can imagine it's an incredible amount of information. The actual event horizon is not a perfect sphere. That it's probably got a microstructure. So if you were to zoom in on it on a very small scale, you would see it's kind of mountainous. And this actually impresses itself on the Hawking radiation. You know, just as your voice, or if you're on the radio, impresses itself on the carrier wave, the radio wave that transmits your voice to the listener. This kind of microscopic terrain actually impresses itself on the Hawking radiation. And it's in this microscopic terrain that the information that describes the original star is recorded. So that's kind of one possible way out. I think that's probably the consensus. You know, you're an astrophysicist, Brian, you must know.
There's so much to unpack in this lovely book. I recommend the audio version because it's. I always like to hear the author's voice. You didn't record the audiobook, but it's close enough to an American's ear that it sounds like you, Marcus. I have to say, it's wonderfully done. Although, and the printed book is as well.
I've actually recorded audiobooks before, so I didn't get asked on it. Well, I really, really enjoyed it. I mean, have you done it? I bet you have.
Yeah, I did it. Well, I did it for 7 or 8 hours of the dialogue between Galileo's world systems with my friend Carlo Rovelli and others. So yeah, we did it. We actually recorded the first ever audiobook of Galileo.
The last one I recorded, it was 2 days in a recording studio. And then the third day we had 1 hour left. And when I got in the recording studio, they said, oh, yesterday when I recorded 8 hours, we had an unexplained hiss in the background. And could you record it again? And I mean, I was in the studio for 10 hours and I was kind of speechless at the end because I thought it was all over, but But obviously there are harder jobs like working down coal mines than recording your audio book.
Or, writing equations in the trenches of World War One. And,
Yeah.
soon I want to ask you what the next great black hole discovery might be, whether it would be in theory, observation, experiment, ranging from quantum gravity breakthroughs to so-called multi-messenger astronomy and observations that we haven't dreamed of yet. But first, to really understand where we're going, we have to look at how we got to our understanding of black holes from the first place, because it's a human story too, not just about cosmic monsters and ruptures in space time, and it involves people like Carl Schwarzschild and Subramanian Chandrasekhar and many others. And I wonder, of all these kind of characters that you got to study, which is the most sympathetic or pathetic, perhaps? There's a lot of sadness. There's a lot of debauchery, or shall I say, kind of skullduggery by some unsavory characters that goes along with it, including the ignorance of underrepresented groups in astronomy to get attention. So talk about the history of the discovery, the theoretical predictions, and the experimental triumphs that led us to the understanding that we have now before we pave paths forward to the future.
So the book begins with Carl Schwarzschild, who was on the outbreak of he was German. He was the director of the Berlin Observatory on the outbreak of the First World War. He joined the German army immediately. He had no need to. He was 40 years old, but anti-Semitism was on the rise in Germany, and he was Jewish, and he wanted to show he could be a patriotic German. He ended up running a weather station in Belgium, calculating shell trajectories. He ended up at a place called Mulhouse, which was on the northern border of France, between France and Germany, the only bit of the Western Front that was mountainous. And in November 1915, he went on leave to see his family in Berlin. And on the 18th of November 1915, he attended a lecture by Albert Einstein. And Einstein, in 4 lectures in November 1915, presented his revolutionary new theory of gravity. And Schwarzschild was completely captivated, went back to the front, and he did something that Einstein thought was impossible. And so what you have to realize is that Einstein had shown, Newton said there was gravity was effectively an invisible tether that connected the Earth and the Sun and kept the Earth orbiting forever. Einstein realized this was incorrect. What a mass like the Sun actually does is it kind of warps the space-time around it into a valley. I said before, you can't actually see that valley. And the Earth kind of goes around the upper reaches of that valley, rather like a roulette ball in a roulette wheel. So gravity is actually the curvature of space. Now, one thing you need to know is that Newton used one formula to characterize gravity, and Einstein used 10. So actually finding a curvature of space for any useful body, like a star, was considered by Einstein to be impossible. But within about a couple of weeks, Schwarzschild, on the Western Front, found the solution, sent it to Einstein. Einstein was amazed to get a letter from the Western Front and then to find there was something in it that he considered to be impossible, and he presented this result at the Prussian Academy of Sciences. But Schwarzschild had not finished and realized that if basically he found the curvature, around a spherical mass, which was the shape of the valley of space-time. And then he realized that if that mass were to become more and more compressed, the valley would become steeper until eventually it became a bottomless pit from which light could not escape. And therefore the object would be shut off from the universe. It would be black. He sent this to Einstein. Einstein presented it again at the Prussian Academy. Never believed in black holes until he died. And there's an obvious reason for that. It taken 10 years of blood and sweat to come up with his new theory, and to discover within a few weeks of presenting it that there was actually a place where it broke down. I told you before that if a star shrinks, there's nothing to stop it shrinking down to a point. We call that a singularity. When everything skyrockets to infinity, the density or whatever, when you get that in a formula, when you get that in a theory, it tells you your theory has been stretched to a point beyond which it's got anything sensible to say. So Schwarzschild, and then sadly, the story, sadly had a disease called pemphigus vulgaris in late December 1915 when he was writing to Einstein. He got these blisters in his mouth. They spread all over his body. Took a long time for him to be diagnosed, but this is a disease in which the immune system attacks the skin. And the skin, of course, is your barrier against infection, against microorganisms. So he knew he was going to die. And he actually went back to Berlin and died in May 1915. But his idea did not die with him. And there's a lot of things I could tell you, but you asked me about people who I would like to talk about. And one of them is Louise Webster, who has been entirely written out the history of science. She was the co-discoverer of black holes with Paul Murdin in 1971. And of course, if you've read my book, you've read my book, of course. I was switched on to black holes at the age of 12 because I was a member of the Junior Astronomical Society, and my dad took me to a talk in London by someone called Paul Murdin, who hobbled towards the stage on crutches. He had childhood polio, and he proceeded to talk about this object called Cygnus X1, which was the first black hole candidate. And it blew my mind. It blew my 12-year-old mind, but it's only recently I discovered that he actually co-discovered it with a woman called Louise Webster. They were both 30 years old. She was Australian, and she went back to Australia. She had liver disease, and she had one of the very first successful liver transplants in Australia, but sadly got cancer, and she died at 49. And she's been completely forgotten. So if you remember anything about this podcast today, remember the name of the co-discoverer of black holes, Louise Webster. And I think you also know that pulsars or neutron stars, these are another collapsed form of stars. So if a star is not massive enough to collapse all the way down to singularity, it can form what we call a neutron star, which is a star basically about the size of I don't know, it's half the size of San Diego, but the mass of the sun, and a sugar cube of material of a neutron star would weigh as much as the human race. So they're super dense objects. They were discovered by Jocelyn Bell, who was a graduate student at Cambridge in 1967. And there have been 3 Nobel Prizes for pulsars, and none have gone to her. So the 2 types of stars, what we call relativistic stars, the 2 types of stars or endpoints of stellar evolution that require relativity to understand, black holes and neutron stars, were both discovered by women.
I had Dame Belle Burnell on the podcast. I had her on December 10th in 2023, which you'll recognize as the day the Nobel Prizes are given away. So I wanted to make sure that at least, we celebrated the proper way. There's one other object that plays it might have been a red herring, or it might have been kind of a false start, but is integral to the story of black holes, and that's their, kind of mirror image white dwarves, at least. The story that you weave so beautifully starts off with a young Subramanian Chandrasekhar traveling and then ultimately getting undercut, and that delaying the progress of not only the discovery of black holes, but theoretical astrophysics for decades to come. He eventually did get recognition with a Nobel Prize, but not until he was quite old. So talk about him, his discoveries, why they're so important, and how they segue into the black hole narrative.
Well, of course, nobody who thought about it wanted to believe in black holes. I mean, this is the story of people over the last century being dragged kicking and screaming, having to consider these objects, because no one wanted to think about the singularity at the center where everything breaks down. And certainly Einstein didn't want to believe it. So anyone after about 1915 who thought about it, which were very few people, thought there's got to be some other force that intervenes, that stops a massive star, or it's the core of a massive star at the end of its life, from shrinking down to an infinitely dense point, to a singularity. There's got to be something that stops it. And in the 1920s, something turned up, which was, of course, what we call quantum theory. Quantum theory is our very best description of the microscopic world and their of atoms and their constituents. It's given us lasers, nuclear reactors, iPhones, basically created the modern world. There's a principle called the Heisenberg uncertainty principle. And all you really need to know is that if you try and compress something like a proton or an electron or whatever into a small volume, it resists. And this is not anything to do with its temperature. It's not the fact that it's flying around because it's got temperature. This is a fundamental thing. And so anyone who thought about it thought, well, actually, and there were people at Cambridge in England, like Ralph Fowler, who thought about this, thought, well, actually, this runaway catastrophic gravitational collapse will be stopped. And then a 19-year-old Indian from Madras, which is now Chennai, I believe, in India, was on his way to Cambridge to do a degree. And he was sitting on the deck of his ship as it went through the Suez Canal. And he was thinking about the death of stars. And he happened to know about a quantum theory, and he knew a bit about stars. And he realized that everyone who thought about this problem had missed out one key element. And that was Einstein's theory of relativity, which basically gives an upper limit to the speed of anything. So if you compress, a star gets the end of its life and it shrinks and its electrons get pushed together, they can push back through the Heisenberg uncertainty principle. They push back, rather like, raindrops on a roof, spattering on a roof. But there's a
pushing New Yorkers.
Yeah, there's a limit. There's a limit to how fast they can push back because they cannot move faster than the speed of light. And he realized that there was actually, if the star was more massive, its name was Subramanian Chandrasekhar. We now call it the Chandrasekhar limit. If a star is more than about 1.5 times the mass of the sun, this Heisenberg uncertainty principle, what we call degeneracy pressure, could not prevent the star from collapsing. So if the star at the end of its life was more massive, a black hole would be the outcome. And as you say, probably one of the greatest astronomers of his day, Arthur Eddington, one of the two people who had understood Einstein's theory of gravity in 1915. The other was Willem de Sitter, who was a Dutch physicist. But Eddington understood it and presented it to the English-speaking world. I remember there was a poll, I think it was in the 20s or 30s in America, of who was the top 10 astronomers in the world. And he was ranked by American astronomers as the #1 astronomer. And Eddington just did not believe in this limit, this Chandrasekhar limit. And it's very hard to understand why he didn't, because he just said, the world does not work this way. Nature does not work this way, which is not really much of an argument. And he did his best to completely undermine Chandrasekhar and, in fact, humiliate him. Chandrasekhar gave a presentation at the Royal Astronomical Society in London, and he did not know that Eddington was going to give the talk after him, and he did not know that Eddington's talk was to entirely undermine him. And poor old Chandrasekhar had to even move to another field of astronomy because he knew he could not compete with Eddington because Eddington was such a powerful figure. But as you just say, in 1983, he was vindicated. He got the Nobel Prize. Eddington died, I think, in the Second World War. Never got the Nobel Prize, but Chandrasekhar did. And he was very hurt all of his life, although he was always said that he admired Eddington. And I was there, actually, on the spot at Caltech when Willie Fowler got the Nobel Prize in 1983 and Chandrasekhar shared the Physics Nobel Prize that year.
So given the fact that I see the black hole story as sort of a relay race, not a marathon, but bold ideas, kind of first promulgated by theorists, outpacing experimentalists and instrument builders. But that kind of, trickles down when we reach the limit of measuring, massive and supermassive black holes. We went, as I understand the trajectory that this subject took, thanks to your book, white dwarfs, then followed by neutron stars, and then eventually pulsars, and then black holes, and theory was always in front. And even it was in front for a long time with gravitational waves. I've spoken to, all three, Kip Thorne, Barry Barish, and Ray Weiss on this podcast, as well as people like Shep Dolman from the Event Horizon telescopes. What do you see as the future of this marriage between theory, phenomenology, observation, instrument builders, of chasing down the impossible? What's going to be the next frontier? Is it some new developments in theory, or have we reached the end of theory? Is it some new technological device that we don't have yet, or is it some huge budget to build larger and larger instruments to the kind of which we do have? Where do you see the future of this field going?
Well, I mean, it's incredibly exciting. So first of all, you just mentioned gravitational waves, which are like ripples in the fabric of space-time. I mean, basically a tsunami in the fabric of space-time, but of course, by the time we pick up these signals, they fill a huge volume of space and become massively diluted. But they were detected on the 14th of September 2015, predicted by Einstein in 1916, because, mass or energy can warp space. It can also ripple it. It can also jiggle it. And knows what gravitational waves are. The first discovery was of two black holes which had merged, and I think they were something like one was about 35 times the mass of the sun, the other one about 50, something like that. This was much, much bigger than anyone had expected. And we're now seeing mergers. We've seen about 100 now, including neutron star mergers and black hole neutron star mergers. And we're seeing black holes which are much more massive than actually could possibly exist. So there is actually a gap, a mass gap, where we do not expect to see mass black holes. And that is because when a star is massive enough, we get what was called a pair instability supernova, and the star blows itself completely apart. So there is no implosion at the center to form a black hole. So we shouldn't see any black holes in a particular range, yet we do see them. So what we're learning is that the black holes we're seeing merging, pairs that we're seeing merging, spiraling together and merging, individually had actually merged before. So this process of merging is quite common. That's going to continue, and we're going to be surprised by what we actually discover. I think probably one of the most amazing things is the James Webb Space Telescope, which is, showing us the pretty newborn universe when it was maybe 2 or 3% its current age. And we're seeing these supermassive black holes, or we're seeing evidence of these supermassive black holes, very, very large, very early on. So we're seeing billion solar mass supermassive black holes within, 300 or 400 million years of the Big Bang. And that's quite difficult to understand, but I think there's some evidence. I mean, there are these things called red dots you've probably heard about, which have been seen, and they may well be black holes enshrouded in a very, very dense shell of material, and so sucking in material at a rate greater than they ought to be able to do. So we may get this pretty soon, I hope, the solution to where these supermassive black holes come from. Now, I ought to just say, what I haven't told you is there's probably a complete spectrum of black holes, from stellar mass up to really large ones, but we basically see two populations. One is stellar mass black holes, which we believe form when in supernovae a star blows itself apart. Paradoxically, the core implodes. In fact, it's the implosion that drives the explosion. And then we see these supermassive black holes, and the biggest ones are something like 60 billion times the mass of the sun. And their origin is a complete mystery. We're seeing them very, very early on in the universe. So we believe that black holes start off quite small. I mean, it could have been an early generation of stars that formed very shortly after the Big Bang. There's a lot of evidence that they would have been more massive than stars today. So it's quite possible they would have gone through their life histories quite quickly, exploded up for produced black hole. Those black holes maybe would have merged, sucked in material, but it's quite difficult to see how a black hole could grow from stellar mass to 1 billion times the mass of the sun in the available time. So that's a really big mystery. I mean, it could be conceivably that they are spawned in some way in the Big Bang itself, in the turbulent conditions in the Big Bang. That would be very interesting. So I think, to answer your question, I think the origin of supermassive black holes that's an incredibly important question to answer. So let's face it, there's one Hubble Space Telescope discovers in the 1990s that there's actually a supermassive black hole in the heart of pretty much every galaxy. In fact, essentially every galaxy. So we don't know what they're doing there. Did they come first? Were there supermassive black holes formed in the universe? And then maybe they gathered material around them, which then collapsed to form stars. So were they the seeds around which galaxies form? Or were the galaxies formed first, and then maybe there were very dense clusters in the center that ended up forming supermassive black holes? So we don't understand anything really about the origin of supermassive black holes. So the story of my book basically is how black holes have come in from the cold. So as you said in your introduction, Brian, at the very beginning, they were so ridiculous as to not even be considered the preserve of science fiction. But gradually, over the last century, they've moved more and more into the center of science. When we realized that they had to exist because we discovered Martin Schmidt at Caltech discovered quasars, which are often pump out 100 times the amount of light of a normal galaxy from a volume maybe the size of the solar system. So that was 1963. Within a year, theorists had realized that there was only one possible source of that energy, and that was material swirling down like water down a plug hole, onto a black hole, being heated to millions of degrees and shining that way, but not a black hole of a few times the mass of the sun, a black hole of billions or tens of billions of times mass sun. So supermassive black holes. But then we thought, well, quasars, they are what we call active galaxies. There's a whole zoo of them. But basically, they're galaxies. We define them as galaxies that are generate most of their light not from stars, but from a accretion disk, what we call around a supermassive black hole. And at that point, only 1% of galaxies were active galaxies. So we could think, well, they're not really important. We can sweep them under the carpet. They're anomalies. And then we discover there's one in every single galaxy. And the reason that we only see them in only 1% of galaxies are active is because in only 1% of galaxies are they being fed. So in 99% of galaxies, they've sucked in all the gas and rich about stars, and they're slumbering. They're slumbering. And of course, there's a supermassive black hole in the center of our own galaxy, although it's a tiddler.
That's right, compared to our big brothers in M87. I want to quote a lyric from the famous astrophysicist, not Brian May, but from Leonard Cohen. And it goes like this: ring the bells that still can ring. Forget your perfect offering. There's a crack in everything. That's how the light gets in. And I interpreted the title of your book along those lines, in that you present black holes as this confluence between all the major ideas of physics, modern physics, quantum mechanics, thermodynamics, information theory, general relativity, special relativity. They all sort of break down at one level or another. How important is that narrative, where the cracks are what reveal the truth, and why we shouldn't, as physicists, be afraid of flaws and cracks in our most cherished theories and ideas?
Well, you've put your finger on exactly what the title means, because, in physics, places where our known laws of physics break down are gold mines. They're really what we look for. We look for paradoxes. We look for places where there are two theories that predict in the same domain different things. Then we know that one or both of those theories is wrong. And there is I saw this survey, a psychological survey, and it was about people who were willing to change their point of view. It was talking about politics, but people were willing to change their point of view. And the people who scored highest, the people who were most likely to change their view, were people with a scientific background. And that is because they actually enjoy seeing, that they enjoy being proved wrong. So really, scientists get a lot of joy out of finding out that their theories don't work, because they're constantly looking for the deeper, better theory. And really, our scientific theories are provisional. They are the best description we have at this moment, but we know they break down. So, to everyone but Einstein, who was not happy with black holes are of gold dust. There if we get contradictions in physics, and we are challenged by nature to come up with a better theory. And the better theory we expect, but we could be wrong, is what we call a quantum theory of gravity, where we unite our theory of the very small, which is quantum theory, with our theory of the very big, which is general relativity. Because in a black hole, something very big becomes very small. A star shrinks smaller than an atom. So we need to unite these to understand what happens in the center of a black hole. And coincidentally, where the universe came from, because we believe that the universe also began in a singularity, although a singularity in time rather than a singularity in space, but similar kind of thing. So yeah, and I was saying about how scientists actually revel in having to change their mind, because really, if you go back 50 years, our picture of the universe is entirely different to the picture that we have now. Imagine how many objects that we know of now in the universe that we didn't know about. I'm thinking of things like gamma ray bursters, which they were known about, but the US military was keeping them a secret, discovered them because it was trying to find the gamma rays produced by clandestine Russian nuclear tests. It was using spy satellites to do that. And it discovered this, a burst of gamma rays once a day from somewhere in the sky. Fortunately, those satellites, they could tell where they were coming from. Otherwise, they would have triggered a nuclear war. And they knew that they were not coming from the Russians. They were coming from space. Black holes are just really challenging us
Yeah, it's a unique laboratory for understanding physics at the extremes. I want to mention something you hinted at before I get to the creation of the universe from black holes. Maybe we can touch upon an interesting theory that you discuss in the book, which, by the way, you don't discuss cosmic natural selection, which we're going to get to in a minute, but you do discuss how our existence might be owed, in fact, to black holes. Can you elaborate on that for listeners that might be shocked again to hear such a wild idea?
This is the greatest irony. So, they start off, as really not even a preserve of science fiction. And they move so far to the center of our picture that we actually think that, first of all, they play some key and still mysterious role in generating the universe we see around us, but specifically in us having this conversation. It comes down to, I told you every galaxy's got a supermassive black hole in its core, and we've got one. It's called Sagittarius A star. It was discovered in 1974, so 51 years ago. Two people in 2020, Andrea Ghez, an astronomer in California, and Reinhard Genzel in Germany, won the Nobel Prize in 2024, working out its mass. And its mass is 4.2 million times the mass of the sun. Now, this is a mystery, because this is really, really tiny. This is thousands of times smaller than the supermassive black holes in active galaxies like quasars. And if we compare the Milky Way with Andromeda, Andromeda is the nearest big galaxy, a galaxy that's a spiral galaxy and very, very similar to the Milky Way. Its supermassive black hole is 50 times bigger. So why have we got such a tiny, tiny supermassive black hole connected to us being here? Because I said in the beginning, in the galaxy with big black holes, they have these tremendous titanic jets that stab outwards from the north and south poles of the spinning black holes, stab outwards often not only millions of light years through space, but sometimes 100 million light years through space. I mean, it's shockingly, how they stay collimated, how they stay narrow for that long is still a mystery. But what in the galaxies with the big supermassive black holes, these jets can drive away all the gas in the center of galaxies. Now, that's the raw material of new stars. So in these galaxies, the star formation is kind of snuffed out after one generation. But it didn't happen in our galaxy because we've got a tiddler of a black hole. We've probably never had any powerful jets at all. And so we've had multiple generations of stars, and our sun is a third generation star. And in each successive generation, which forms from the raw material, of the exploding stars of the previous generation, in each successive generation, more heavy elements are forged. So more carbon, more oxygen, more iron, more calcium.
That brings up this little artifact that I give away to my listeners. If you go to briankeating.com/list, this is a meteorite, which is a fragment probably of a population 2 star that eventually coalesced to be a part of our solar system as a bridge between the earlier and later generations. So these stars give their lives to make our lives possible.
Yeah,
right?
and only because of our small black hole, it has been possible for there to be multiple generations of stars. And I just listed those elements, and those elements that have been forged because we've had multiple generations, because we have a small supermassive black hole, those elements are precisely the ones needed to make your meteorite, to make a rocky planet like the Earth, and to make biological life like you and me. We could not be having this conversation in, for instance, M87. You mentioned M87. This is a nearby galaxy with a 6.5 billion solar mass black hole. Image was publicized in 2019, the first ever image of a black hole. And we could not have arisen in that galaxy. So we believe that galaxy is probably a biological desert. It's remarkable that we've come from thinking that these objects were so ridiculous as not to be the preserve of science fiction to thinking that we're having this conversation because of a black hole, Sagittarius A star.
And that brings me to this provocative question that I've been teasing the listeners about since the first few seconds. We started off the conversation with a description of black holes as predators, as paradox machines. And I promised I'd come back to this idea that the black hole might not be the end of the story when it comes to producing life on Earth. What about if it's the cause not only of our existence on this wonderful podcast, but of entire universes like our own within the multiverse? And just for the readers and listeners that are not familiar, rather, Lee Smolin, past guest on the podcast, proposed that black holes might actually spawn new universes, each one with slightly mutated laws of physics, a kind of cosmic natural selection. He calls it that, in fact, CNS. Now, I noticed in the book, I didn't see it, and that was a little bit surprising. I don't believe you mentioned cosmic natural. You mentioned Lee. Lee is in there, I think, 1 or 2 times. But I'm curious, first of all, why didn't you mention it? Was it a little bit of a bridge too far, or is there actually some justification for treating these black holes not only as, fertilization within galaxies for life like us to exist, but also for universes onto themselves to exist. In other words, within the multiverse, to explain the peculiar qualities of our own. Is this a bridge too far, or are black holes not tombstones, but rather cosmic universal cradles?
I think it's a bridge too far. And the reason is that my book is principally about real black holes, black holes that we've actually discovered. So it's the, it culminates with, you mentioned the Event Horizon Telescope, getting the first ever images of Sagittarius A star and M87, the black holes. My last chapter is about speculative ideas, but I didn't mention this one. And one of the reasons is that we really don't know what it's like inside a black hole. So I've got the stories from people like Paul Merding, who was the co-discoverer of stellar mass black holes, and Roy Kerr, who was a really interesting character. He's now 91 years old. He basically came up with the first development in Einstein's theory of gravity for 47 years. And he did something which people thought was impossible. He discovered the shape of the space-time around a spinning black hole. Now, I told you, everything in the universe is spinning. So actually, Schwarzschild had come up with the shape around a static black hole. So that wasn't very realistic. So he came up with a description which describes every single black hole in the universe. He was 29 at the time. He himself gave up on working out what the space-time was like inside a black hole because the problem was just too difficult to solve. So we really don't know what it's like inside a black hole. Not only can we not solve Einstein's equations to find out what the shape of the space-time is inside a black hole, but we certainly don't know what it's like near the singularity, because the singularity doesn't exist, by the way. I should tell you that. When a singularity appears in a theory, it tells you your theory is broken, you need a better theory. So we need a quantum theory of gravity to tell us what exactly is at the center of a black hole, and we don't know what that is. So saying that it connects to another region of space-time, that it's a time machine that generates another black hole or another universe, this is so far removed from what we can confidently talk about that I didn't really smooth it. There's loads of other books about black holes. Most books about black holes are about theoretical black holes, about Hawking radiation. I love Lee Smolin's idea. I hope he's correct. But again, it's not very well founded. And the problem is, once you start admitting not very well founded ideas into this, you have a book which is 100 times longer than the book that you were writing, and people get lost. What do we know and what that we don't know? My thought is really that the things that we know are so fantastic and so amazing that we don't need to really speculate anymore. Again, if you if I'm thinking of something else like dark matter. So with dark matter, which was this invisible stuff that fills the universe, outweighs the visible stars and galaxies by about a factor of 6, we can speculate, and there's literally hundreds of speculations as to what that dark matter could be. But it doesn't really get us anywhere, and the reader then gets confused by all these hundreds and hundreds of possible suggestions, none of which are constrained by physics, because we've never detected any. So yeah, no, I think Lee Smolin wrote a wonderful book, didn't he? It was called, what was it called now?
The Life of the Cosmos.
Yeah, about black holes. Yeah, so basically he says that the conditions necessary to create black holes, the laws of physics necessary to create black holes, are also the laws of physics necessary to create biological life. So that the two are hand in hand. So the universes that create the most spawn the most black holes, I think that's correct, isn't it?
Produces constants of nature and laws of physics that are compatible. It's an anthropic, what's called a weak anthropic.
Yeah, obviously, as Einstein said, the most incomprehensible thing about the universe is it's comprehensible, which is a fantastic remark, isn't it, really?
Well, one thing I appreciated with bittersweetness was you're mentioning the Bicep 2 affair, which I played a not insignificant role in. And it made me think of some of the more, again, there's a lot of, pathos in these. Our mutual friend, Jan Levin, who you write about in the book, has written, Black Hole Blues about the, kind of stories of the unsung heroes, the lovable losers and so forth. And one of them, which I resonate with, no pun intended, actually pun intended, it was a good pun, is Joseph Weber. So he, of course, was, claiming that he had detected gravitational waves, 3 or 4 decades before LIGO actually did it. And it was only because of a slight amount of hubris, I think it's safe to say, that on his part, that he never really gave up the belief that he had discovered these first. And it made me think about all the false starts and the curious characters in this book. You mentioned Louise and you mentioned Jocelyn Bell and others, but are there other stories maybe that didn't fit into the book or perhaps would be in an additional book? Are there other, sort of human stories that were neglected, because we look at the black hole and it's not unlike a black mirror. We learn about the subterfuge and the chicanery and the stolen credit and the stolen valor in this book very delightfully. Were there other characters that you didn't get a chance to disclose that maybe the public would have a desire in knowing more about?
Popular science writers tend to write science as if it's like a, one-way street. Everything, it's a logical timeline. But in fact, scientists are human beings. They propose the existence of things for the wrong reasons. Progress of science is like a drunkard's walk, a few steps forwards, a few backwards, I mean, your subject, I know, is the cosmic background radiation, which is the afterglow of the Big Bang. My first popular science book was called Afterglow of Creation, and I went to interview lots of people who are now, unfortunately, now dead. I talked to Robert Wilson, who discovered the microwave background, to people like Bob Dickey and David Wilkinson, and all these kind of people. But I mean, interestingly, one of the great figures was George Gamow. He basically came up with the idea of the hot Big Bang. I mean, common sense, I suppose, tells you that if the universe was smaller, it would have been hotter, because if you squeeze the air in a bicycle pump, it gets hotter. But no one had really thought seriously about that. So Edwin Hubble discovered the universe was expanding in 1929, which meant that if you ran the history of the universe back in your mind's eye, like the movie in reverse, you would come to a point when it was all compressed into a small space. You now call it a Big Bang. But no one really thought more about it. It was so ridiculous to think that they could think about physics then. But then we get George Gamow, who was a Ukrainian American physicist, and he was very interested in where the chemical elements had came from. There was a lot of evidence from the early 20th century that the universe had begun with the simplest element, and all the other elements, 92 naturally occurring ones, had been assembled by these atoms or nuclei coming together. But that required a lot of heat. Turns out that the nuclei, the cores of atoms, are positively charged. And when you try and thrust together two positively charged nuclei, that they really repel ferociously. So you really have to smash them together at very high speed, and that means high temperature. We just mentioned, by the way, Arthur Eddington, and one of the greatest British astronomers, but he had made a mistake, and he thought he had an idea that elements could not be built inside stars. By this time, they knew by about the 1930s that hydrogen nuclei, the cores of hydrogen atoms, if they were glued together in a multi-step process to make the second heaviest element, helium, this would liberate enough energy to explain sunlight or starlight. But he thought, Eddington, that as the sun rotated, there would be currents, what we call meridional currents, which would kind of spread out that helium. So if you imagine the helium is the ash, so basically this would actually cause stars to fizzle out. He had managed to rule out stars as the place where elements were built. So Gamow was thinking, where else? And this is when he started thinking about the universe. When it was small, it would have been very hot. And he thought, that's just it. That's the place, And he got his two students in Washington, Ralph Alpha and Robert Herman, to work out the details, because Gamow was not a details man. He came up with a lot of brilliant ideas in his life, but he was not a details man. And they worked it all out. And they realized that, incredibly, you could actually end up with 10% of the atoms in the universe as helium, 90% hydrogen, but you couldn't get really beyond that at all. So you could, and it turns out that 10% of the atoms in the universe are hydrogen. So again, so he comes up with the idea of the hot Big Bang for entirely the wrong reason, but he's correct, you know. And then again, when people started searching for this afterglow, there was a team at Bell Labs in Hangzhou in New Jersey, and there was also a team remarkably only about 20 miles away in Princeton, and they had a little radio dish or radio horn on their roof. The leader of their team was a guy called Bob Dickey, and he had the idea that the universe was pulsating. You know, it was so he
Cycling.
yeah, like a cyclic universe, like a giant beating heart. So there would be a big bang, it would expand, gravity would eventually collapse it down to a big crunch, and it expand again. And he realized that this beating heart universe would have radiation over. You know, there'd be something like 10 billion photons for every particle of matter or so. So his team was looking for this afterglow for entirely the wrong reason, because the universe we don't believe the universe has pulsated like that. This has happened with the discovery of planets. I mean, the first planets were found around a pulsar, weren't they? I can't remember.
Yeah, there was a planet around a pulsar.
Yeah, right? Obviously, there couldn't be any life on them because a pulsar is a super dense object with a lot of radiation around it. But this triggered people to actually look at real stars, you know, because they detected it by the wobble of the star. So the pulsar was moving backwards and forwards because it was being periodically tugged from one side and the other side by a planet. And this got people looking at real stars. And sure enough, they began to find planets. And now we've probably got 5,000 or 6,000 extrasolar planets that have been found. So again, you know, there's all these accidental things that actually happen. I really love this, the way this worked. One of my heroes is Fred Hoyle, who was at Caltech, but he in fact cracked the problem of where all the elements in your body come from. He found about 8 or 9 nuclear processes in stars that made all the elements. He put together some pieces of information. He was working on radar during the Second World War. He came to America. In that time, he was supposed to be doing war work, but he went to California. He met an astronomer called Walter Baade, who was at Caltech. Baade gave him some papers on supernovae, stars that explode. And on his way back, he got delayed in Montreal because of bad weather. And he bumped into a lot of people that he knew from Cambridge. And he knew they'd been working on a project called Tube Alloys, which was the British project to build an atomic bomb, you know. So he knew, and he gathered from reading between the lines that there was a problem. There was a problem that they had a problem trying to build an atomic bomb, and he couldn't think what the problem could be. He knew that one of the elements that would be used was plutonium, and he realized that plutonium, as you push 2 bits together to get a critical mass, would generate so much heat that it would push itself apart. So the only way you can actually create the nuclear reactions of a nuclear bomb was to implode this stuff. In Baade it had realized that supernova were exploded by the implosion of stars. And he put the two ideas together, and he thought, is it the implosion of a star at the end of its life that creates the billions of degrees necessary to meet heavy elements? So the idea had come from the atomic bomb. So it's just weird the way all the ideas come together. And he was able to show in about 1946 that you could, in what we would get what's called nuclear thermodynamic equilibrium. Basically, the relative abundance of elements would freeze out, and he was able to show that the relative abundance of these elements like iron and nickel and all these was exactly what we'd observed. And so that was a piece of information which came from the atomic, is just being delayed in Montreal, that bit of information that gave him, he was able to predict the relative abundances of some elements. And then he came to Caltech in 1953. And the reason he came to Caltech was because he was at a conference in Italy on galaxies, and Walter Baade had presented a result in which he realized that the distance indicators, there were 2 types of what we call Cepheid variables, and we had not realized there were 2 types. And if you realize this, you realize that in fact the universe was twice as old as we had thought. And he had presented this in a paper, but there were 2 people in the audience who then quickly published a paper with Baade's result as if it was theirs. And Hoyle had been sitting there because they didn't have a secretary to record the the results, and he was able to prove that Barder had had his ideas stolen. And Barder was so pleased that when he went back to Caltech, he wrote to Hoyle and said, I've persuaded people here to have you come over. Would you like to come over? He went over, he met Willie Fowler, who was a nuclear physicist, and he had a prediction. You probably know this prediction, that the problem in building up the elements is when you get to helium, if you stick two helium nuclei together, you get beryllium-8 and it's not stable. So how do you get to heavier elements? So he thought maybe occasionally 3 helium nuclei collide at the same moment. It's like, you know, in a supermarket car park, 3 people with their shopping trolleys all collide at the same time. And if this reaction with what we call resonant, then you would get the formation of carbon, and then you could build all the heavy elements. And he went to Willie Fowler, and Willie Fowler was a nuclear physicist. And there's something that physicists will never admit to you, and that is that they've only ever solved one problem exactly, and that's the two-body problem. So they've only solved that problem of an electron going around a proton in a hydrogen atom, the moon going around the Earth. That's the only problem they can solve exactly. Once you get to 3 bodies or more, it's not possible to solve it exactly. It turns out that a nucleus of carbon has 12 particles in it, 6 neutrons and 6 protons. This finding out anything about it, like its energy states, was impossible. And this guy from England with round spectacles turned up in Willie Fowler's lab at Caltech, and he said something that no nuclear physicist, or he claimed something that no nuclear physicist would ever claim. He said it's got an energy state at this particular level, because he knew it had to in order for 3 helium nuclei to come together and make carbon-12. And there was a discussion, and they realized that they had measured the properties of carbon-12, but if it had they might just have missed something. 3 days later, they found the carbon-12. He's the only person to have made a prediction ahead of what you call an anthropic argument. So his only argument was, we are here, we're made of carbon, therefore this state of carbon must exist. So I mean, he's the only person.
The so-called oil miracle.
And of course, the other thing is, of course, he actually coined the term Big Bang and never believed in it.
And he worked very closely with my late great colleagues, Jeff and Margaret Burbidge.
Absolutely. He was considered to be a rather difficult character and a bit of a loner, but actually history shows that he had incredibly loyal colleagues that he worked with over long periods of time, you know, Margaret and Geoffrey Burbidge and Willie Fowler. And then when we mentioned earlier that the Nobel Prize, Chandrasekhar getting in 1983, and so did Willie Fowler. And that was very desperately sad for Fowler and Hoyle, because they were such friends. And Fowler knew that Hoyle should have shared the prize with him, because had it not been for that visit to Caltech in 1953, Fowler said, I would have been a run-of-the-mill nuclear physicist. In fact, he actually worked out he'd actually been able to prove the what we call the carbon, nitrogen, oxygen cycle, which generates heat in massive stars. So he had done something, but the actual discovery of where all the elements came from, that was due to Fred Hoyle in 1953. So, you know, that was so sad. Hoyle told me that he was very, very upset for 3 days. And then, like Gothlin Bell, he said, well, I know the history books will remember that I did this. But it was very, very sad, because I mean, there's a man called Jacob Bronowski who did a big TV series in Britain, and he said a genius is someone with 2 good ideas. Hoyle had 2 good ideas. He came up with steady state theory, which was wrong, but it was testable. It was testable, and it turned out that the universe was born in the Big Bang. And he was wrong, but it made testable predictions, and of course he figured out where all the heavy and all the elements in our body come from. So he certainly had 2 good ideas.
Marcus, this has been a delight. I think of you whenever I think of very clear, crisp explications that turn math and mystery into meaning for telling the human stories. And I think black holes are, in a sense, the universe's refusal to explain itself. You can, as your late great friend at Caltech, Richard Feynman said, you can dance with nature, but she won't let you dip her and lift her veil, something like that. And I want to just thank you for the great work that you're doing. And where can people find out more about you?
Thank you very much. I've really enjoyed our conversation. Well, I've got a website called www.marcuschown. So it's marcuschown.com, C-O-M. And you can get my book if you want from Barnes & Noble or Amazon or any of these places, hopefully in bookstores in America. We had a real problem recently. We had the publisher had a cyber attack. So
Oh, no.
they weren't able to reprint that. I think they've reprinted by now.
Maybe it fell into a black hole,
Yeah.
the cyber. Marcus, thank you so much. I'll let you get back to your evening. And I just want to thank you again for this wonderful book, A Crack in Everything. And that's how the light gets in. So now we'll ring the bells that still can ring. Thank you, Marcus.
Thank you very much, Brian.